Today, we're going to be covering a pretty cool topic, one which I find pretty interesting. We're going to be covering modal analysis. Does anyone know what modal analysis is by any chance? It's here on the ANSYS static structural thing that we've been looking at.
Frequency.
Yeah, that's it. It's about finding the modes of different aerospace structures, right? And this is really important when you're maybe deriving loads for components, or you want to see how it responds to a certain vibration environment. So yeah, it's a pretty useful tool. And we're just going to be starting with and going over a pretty simple class example just to show you how to run it in ANSYS actually. And then I think I'll make a homework problem related to modal analysis, but I think it's pretty exciting. So standard, we're starting off everything. This should be like, bread and butter now. We'll make it out of 61. So ARL61, MATLAB, going to define the data properties. And so we always say, okay, make sure you're defining density. In modal analysis, it's especially important that you define density. If you don't define a density, you actually cannot run the sim. So we're just going to go ahead and define modulus 68.9. And if you ever get weird results initially, it's probably because somewhere you may have had like a unit error when you were defining your material properties. But okay, so yeah, we've defined 61 here, and I'm actually going to leave structural steel here as well. If you look at the stiffness of this, you can see that this structural steel and steel in general is stiffer. I'm not going to define a structural steel here, but you'll see why I have two materials defined hopefully shortly. Okay, so I'm going to go ahead and open this model. Okay, so I quickly just catted up a tuning fork. I can send this model as well if you were interested, but this is just to show you the basics of how someone might run modal analysis. I thought a tuning fork was it's something that you see every day where you hit resonance and you hit some frequency, and if it vibrates at a certain speed or angle, you'll see a glass or whatever vibrate in resonance with it. So standard with everything, we're going to change this to 61 initially. And also critically, when I was in the static structural module, I went and dragged in a modal analysis. So we've been doing, we did static structural. Your homework is a transient thermal, and that's what we did last lecture. Now we're doing modal. So hopefully, this is being useful to help you guys build up the toolkit for stuff you might see in industry. So I'm going to define, this is all just default mesh. I define my material property and this default mesh. Okay, and now I'm going to run a modal. So with a modal, you can see it's not really asking for any boundary conditions. And actually, an interesting thing is you don't need boundary conditions to run a modal analysis. You can actually run it with it not constrained at all, and it would solve, which is unlike static structural, where everything must be, everything must close out. The degrees of freedom must make it so it's a static model. But what we're going to do is we're going to try to put something analogous to maybe if you were holding the tuning fork. So I just right-clicked, I added a fixed support. I'm just going to add it on these three surfaces. And the way I did it is, I'm using a face select, so Control F, and then I'm holding Control so that I can select multiple faces. Okay, and now I'm going to apply it. So I'm going to run it, but there's going to be an error, or at least I hope there's an error. All right, and I'll probe you guys and see what you guys think the error might be. So the way you get, so it ran pretty quickly. This is a pretty simple model. The way you get, your results is you can add a deformation. You can right-click this, and now we can retrieve this result. So this will be hopefully our first mode, and this is the mode shape we're getting. Does this seem realistic? No, right? We can play this, and you can see it's kind of deforming that. So what do you think the error was in our setup? There was an error. It might be hard to catch, but similar to stuff we've been talking about in other classes. I'll give you a hint. So there was a warning message here. Yeah, it's a poor mesh, right? So we only have one element here, right? And this, if you look at this mesh, right? This mesh sure is looks like a pretty good mesh, like pretty, linear and stuff, but we haven't given really ANSYS enough elements to understand, the through thickness, what's happening, right? There's generally recommended practice is whenever you have a thickness of a shape, you need multiple elements through it. And right now you have one element through it. So ANSYS is kind of breaking here, right? And you might see this is why, we need better refining tools. ANSYS's default mesh here failed and gave us a wrong shape. So, simple thing that we've talked about on how to improve meshes is you can generally improve the density of a mesh, which increases how many elements there are. So I'm just going to go like 0.1 here, and then right click and re-update this mesh. Okay, so that seems like a better mesh. Again, if you want to see generally how your mesh is, you click element quality, and it shows red, but that's 1 out of 1, so pretty solid. Okay, I'm going to click solve again. And what do you think it'll work? Is there anything else we're missing? I guess we'll see. You can click. And look, we actually did get a mode shape here, which is pretty exciting. And so one thing, I'm going to actually delete this. This was before. So whenever you want to show your results, you can see that, in this graph, we have some results here for what these, the frequencies are. I'm going to right click, insert deformation. And what the deformation allows you to see is sort of how visually these mode shapes look like. And if you have a different structure, they'll look different, right? You might have a torsional mode, you might have a bending mode, you might have whatever. It might be a mixed mode shape. So it's not always as simple as what we're making here, but those mode shapes are really important when you're doing structural analysis. So I'm going to click total deformation here, and you can see that there's only one mode here. But if change the mode shape, I can change it to mode shape 2. Then I can, this is the second mode shape, right? I can go to mode shape 3, and that's the third mode shape, right? But another tool that I like doing is if you right click, you can see this create result at all sets. So it's going to create results at all the sets and modes that you requested, right? And so if you go into analysis settings, here I've said these are the max modes I want to find. So it's going to run until 6 modes, right? But if you're working, you might want to be like, okay, instead I want 20 modes, right? Or I want 6 modes, whatever. We're going to leave it at the default 6. Oh, I guess that's good. But yeah, that's how you get multiple and more mode shapes, right? Of course, okay, I don't know why that broke. Okay, weird. But yeah, you can click the create results at all sets here. And so what this does is now I can evaluate at all results. This gives me all the different shapes, and I can just go through them. So let's go through them and see what they look like. This is the first mode shape. You can see what kind of mode shape is this. Any thoughts? Bending, right? It's pretty clearly, we're holding the tuning fork at the end, and this is one of the mode shapes, the bending shape, right? And you can see the frequencies that these mode shapes occur at here, right? And so if you output 20 mode shapes, you could get 20 different frequencies that these modes would occur at, right? This one is kind of bending, but in the other direction, right? So I think it's cool to look at all these different mode shapes. And as you go, as you keep going through your frequencies, you're going to get mode shapes which are less and less likely to occur. But you can see this one's kind of funky. But yeah, I think this is like a torsion and bending mode shape. It's kind of some torsion on this. Torsion is just like rotation from 2 to 4. Yeah, but okay. So now next question. So I'm currently making it out of 61 T6. What would happen though if I change this to a stiffer material? What would happen to the frequencies that we're looking at? Any thoughts? Semi-related to 302, semi-related to 204. You can see it. We can see what happens. What's there? Yeah, it could increase. Yeah, let's see what happens. Let's run it. So all I did right now is I went to my solid and I changed it to the structural steel. So we looked at and it had a higher stiffness, right? But structural steel is also more dense, right? So you can derive the equation. It's like square root, I think, E over M. That's how you figure out, your natural frequencies. And what you can see is, actually, does someone remember what the first mode was in frequency? I forgot. I'm going to go switch it back, see what it was. Yeah, it's about the same. So it shows it's not just dependent on stiffness, right? 61 versus steel, will have probably similar mode shapes. Let's see. Yeah, it is pretty similar. But let's go in and just change stiffness now, right? Because with steel, you're changing density and you're changing the stiffness, Young's modulus. So let's create a theoretical 60-61. We're just going to 2x the stiffness of 60-61. We're going to keep everything else the same. All right, so 68.9, let's just go to 140. And we're going to keep everything else the same. Okay, and then let's just reopen our model, right click update. Okay, model's updated. Okay, so now we're here, and we have 61, but we have this new 60-61 times 2. This is not real material. Let's see what happens to the mode. So it was around 397 before, right? You can see that the natural frequencies and the mode shapes, they went up the frequency, right? And it's scaling with root E, proportional to root E. Right, so it's not precisely double, would be around 800, but it's gone up by 150, so it's scaling with square root E. So this is pretty useful. You can do this on more complicated structures as well. It doesn't have to be a simple tuning fork, but I thought this was a good example of simple geometry where we can extract the modal results. Anything you want to add, Professor?
Yeah, I want to talk about this quite a bit actually. So let's try to understand the idea of frequency and mode shifts and why that's important, right? So what you have shown here is how we can actually implement this in a software, but why is this so critically important to aerospace structures in general is because you will have various forcing frequencies that will drive the response of the structure that can be damaging to the structure. So let me go through some of those examples. So for example, if you're designing an aerospace structure, obviously has wings, right? And if you look at the fundamental modes of the wing, you will see that's primarily bending. So in this case, it will behave like this tuning fork here. And there will be another mode called torsion that gets coupled with bending for a wing. And what occurs there is that when you have significant amount of turbulence, is going to now, that forcing function that's coming from the wind, the aerodynamic environment, is going to drive the motion of the wing, the amplification that occurs in that wing. Another example we have here is the engine itself, the engine of an aircraft or even a liquid rocket engine. In those two cases, you have the spin motion of the turbine wheel, and that spin is going to have RPM. So you're going to have frequencies that are being driven by the shaft rotations, and that shaft rotation can then now potentially interact with the bending modes of each of the blades of that blisk of their turbine wheel. Because that turbine wheel is like a fan, and each of these blades can bend. And so you're going to impart a significant amount of dynamic environments into each of these blades. That's the second example. The third example is if a launch vehicle taking off, you're going to have significant amount of engine vibrations that go up and down the vehicle. You're going to have the aerodynamic environments acting on the vehicle. And these two loads combined will cause the mode shapes of the vehicle to be excited. So what that happens there, we need to consider that dynamic amplification that occurs due to these input environments. And we'll be covering that later on, and that I'm glad that you went over this. This is teaching you how to get the frequencies of this system. And now when I look at this, the question becomes what I do as a designer with this information. Because anybody can plot mode shapes, right? I mean, obviously not anybody, because as you can see, you can create, results are not meaningful. But if I'm a designer for this particular part, what I want to do then is to make sure that when I design this critical part, that the mode shapes and frequencies of this system are sufficiently separated from the fundamental frequencies of the forcing function. Because if the two interact, you get resonance conditions. And resonance will cause this tuning fork to blow apart. So what we're teaching here is a very important analysis that we do in industry to be able to make sure that we're not driving failure into a part. I'll give you another example where I've seen the most failures. And this is tubing in a launch vehicle. Tubing also in aircraft and other applications. So a lot of times you have tubing, significant amount of tubing across an aerospace structure. If the tubing is not sufficiently supported, then you're going to have, say you have 12-inch no support or 13-inch. The longer you go unsupported, the more frequencies are going to come in, and the fundamental frequencies of that tubing will drop lower. Because if this was longer, the fundamental frequencies will become lower. So what happens? Because now you have more frequencies that are potentially available for the system to get excited, a lot of times these tubings will blow apart the minute you run the engine, because now you have more modes to be worried about. So what you're doing in design, you try to keep the fundamental frequencies of the tubing by providing support. You bring the supports closer, so the fundamental frequencies now of the tube are higher now. And by them being higher, now you're pushing the frequencies so they're so far away from the forcing functions that you should not have a problem. So this is an important aspect of design that we're trying to teach you here. And hopefully the next project is actually looking at a tube. I think that's an excellent example. We can do it pressurized, unpressurized, so they can see the pressure stiffening. When you have pressure inside a tube, you'll see frequencies are higher. But when you have no pressure inside a tube, you'll see the frequency will be lower. And we can maybe look at different supports.
Yeah.
Maybe that's just an idea.
Yeah.
But very important in design, and that's why we want to bring this in. And I'm glad you went through this today.
Yeah, and
You want to add anything to what I said?
Yeah, exactly. The thing that the professor said is, if you have a lower supported length, you can see what I just did. I just changed the fixed support to just this end, and look what happened to the frequency, right? They were around like 600. I reduced the supported length, and you can see they dropped a lot. Now they're like 161, 484. Like this is way lower than what we had before, right? And also the same thing is, if you, like the professor said, if you make it longer, what are you actually doing to your geometry? Sure, the Young's modulus, the material is the same, but the stiffness is changing, right? The bending stiffness of your part is changing, and your bending stiffness is lower. And so if it's proportional to root E over M, because E is now like the actual stiffness is lower, you're going to be seeing lower frequencies.
Excellent. Thank you for the tutorial. Do you want to add anything more?